In this statistics lesson, we will be discussing the addition rule. Please press pause and read through today's objectives. Two events that cannot occur at the same time are called mutually exclusive. You will see a Venn diagram representing that on the left. Notice that events A and events B have no overlap, meaning that they do not occur at the same time. They're completely separate from each other. We call those independent events. A and B could, however, if they are not mutually exclusive, have some overlap where there could be events that are both events A and events B at the same time. So it's very important that we understand whether we are dealing with a mutually exclusive event or a not mutually exclusive event. So let's do some examples. Can you roll a 3 and roll a 4 at the same time? If the answer is no, then those are mutually exclusive events. 3 and 4 cannot happen at the same time. So, mutually exclusive. Can you randomly select a male nurse, a male student, and have them be a nursing major at the same time? The answer is yes. So those are not mutually exclusive. There will be overlap. You can have males that will also be nursing majors. Can you randomly select a blood donor with type O and have them be a female donor? And the answer is, of course, is yes. You can have type O blood and also be female. So those would not be mutually exclusive because they can happen at the same time. All right, and we need to know this mutually exclusive events because we need those to talk about the addition rule. The addition rule for a probability is the probability that event A or B will occur. That formula is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now, if the events are mutually exclusive, then the probability of A and B will be 0 because there will be no events that will both qualify for as event A and event B. So in that case, then the formula gets shortened a bit. But if they are not mutually exclusive, you will have to use that formula at the top. So, say you have a deck of cards and you want to find the probability that you have a 4 or an ace. Notice we have a nice Venn diagram. You cannot have a card that is a 4 and an ace at the same time. So these two events are mutually exclusive, which means I can use that shorter formula. So probability of a 4 or an ace. So that would just be the probability that you draw a 4 plus the probability that you draw an ace. There are 4 cards that are the number 4 in a deck of 52, plus there are 4 aces in that deck of 52. So that gives me 8 out of 52. Again, if they wanted an exact answer, you could leave it as a fraction. Just make sure you simplify this fraction, but most want a decimal, again, because probabilities are usually written as decimals. So you have about a 15.4% chance that you will draw a 4 or an ace. All right, if you roll the die, find the probability of rolling a number less than 3 or rolling an odd number. So again, we have the odd numbers are 1, 3, and 5. Numbers less than 3 are 1 and 2. And then we have 4 and 6 that are outside that because they don't fit into either category. But notice we do have some overlap. So these events are not mutually exclusive because the 1 is both odd and it is less than 3. So we have to use the longer version. So probability that we have a number less than 3 or we're rolling an odd. Okay, so that is going to be the probability that the number is less than 3 plus the probability that we roll a number that is odd minus the overlap. The probability of number less than 3 and it's odd. So that's your overlap. So here we go. We have a 6 number space because there are 6 sides on that die. So numbers less than 3, there are 2 of them. So that is 2 over 6 plus the odds. There are 3 out of the 6 minus the overlap, which is the 1. We had 1 number out of the 6 that was overlap. So that gives me 4/6, which if they want you to simplify it, that's 2/3. But usually they want that decimal. So 0.667 if you round to 3 decimal places. All right, you might be given a chart and be asked to find this information. So here's a frequency distribution that talks about the volume of sales in dollars and the number of months in which these sales representative reach each sales level during the past 3 years. Okay, so using this pattern, using this frequency table, find the probability that the sales representative will sell between 75,000 and 124,999,000. So we've got these two to look at. There's that, and there's that. Okay, is there any overlap between those two? There is not, and that frequency distribution sets that up so there should not be any overlap between those two classes. And if you remember that from earlier when we talked about frequency distributions. So for this one, we just want that we'll just call this event A and this event B. So we want A or B because they are mutually exclusive. We're just going to add their two probabilities together. So probability that we get that 75 range, that would be 7 out of the, let's see, add all these up. And that was 36 months, which makes sense because that they're talking about 3 years, right? Past 3 years, so 36 months. So 36 plus B, we had 9 months out of the 36. So that gives me 16 out of the 36. Which again, you could simplify to the fraction, but again, most want you to write it as a decimal. So 0.444. All right, here is a chart that talks about blood types and your Rh positive or negative status. All right, and they want you to find the probability that a donor has type O or A. All right, so type O or type A. You cannot be both. You are one or the other. So these two are mutually exclusive. So the probability that we have O or A blood is equal to the probability that you have type O plus the probability that you have type A. So out of the 409 people, we had a total of 184 that had type O, and out of the 409 people, we had 164 that were type A. So that gives me 348 out of 409, which again, if you wanted the decimal, that'd be 0.851, which most textbooks use the decimals when we talk about probabilities. All right, so again, utilize that chart. Let's answer another question about that chart. All right, find the probability that the donor has type B or is Rh negative. Okay, so first ask yourself, can you be type B and Rh negative? And the answer is yes, because if you look at the chart, we've got type B and Rh negative. There aren't many people, but there are some. So these are not mutually exclusive. So the probability that they are B or they are negative would be the probability that they have type B blood plus the probability that they have an Rh negative minus the probability that they are both B and Rh negative. So probability that they are type B, there are 45 people out of the 409 plus Rh negative. So we got to go to this row, this row right here. There are 65 people out of the 409 that were Rh negative, and then subtract the overlap, which is these right here, type B and Rh negative. So 8 out of the 409. So add those all up, and you get 102 out of 409. If you can simplify that, do, but I'm going to go right to that decimal, 0.249 approximately. All right, so far in our probabilities, this is everything we have kind of talked about. We have the 3 types of probabilities, our classical, our empirical, and then our, educated guess. A lot of people don't put that on the summary, but I still think it's important that you should have some educated guesses in there. Remember, your probabilities are always between 0 and 1, 0 being impossible events, 1 being certain events. Don't forget about the complements we have talked about, the multiplication rule, and the addition rule. These are all needed because when you get problems, they're not always going to be super straightforward. Sometimes you're going to have to combine all of your knowledge to figure out what's going on. So let's do an example of that. All right, so this is the figure that was in the newspaper. You need to figure out the probability that a randomly selected draft pick is not a running back or a wide receiver. So rather than focusing on the not, because that tells me we're going to do some complements down the road, let's just focus on our two. So if they choose a running back, let's call that A, and if they choose a wide receiver, let's call that B. Those are our two events. All right, can someone be drafted as a running back and a wide receiver at the same time? They cannot. You are drafted for a certain position. So these will, so if I want to find the probability of A or B, I would just take the probability of A plus the probability of B. And that would tell me that. So let's find that out. So let's see, how many running backs did they, let's see, running backs is right here. There were 16 running backs, 16 out of the 255 players. Notice that was also given to me right here. So make sure you're pulling out as much information from your graphics as possible. Plus, B is the wide receivers, and wide receivers are right here. That's 37 out of the 255. So that is 53 out of the 255, but that's not what I'm trying to find. I'm not trying to find the probability that I had a running back or a wide receiver. I am trying to find the complement. So my complement is going to be 1 minus the probability of A or B. So 1 minus 53 over 255 is going to be 202 over 255, and again, if you put that as a decimal, that is 0.792. So notice we had to combine both our addition rule and our complement rules to make this problem work, and that's the type of problem that you should be ready for, ones that you have to use all of your knowledge to get those together. All right, so let's say that you were trying to figure out which of the three drive-through restaurants in town had the best drive-through service. So you sent random people in to go through these drive-throughs and then just say, was your order correct or was it not correct? And you just collected all that data. So here's a chart representing all of that data. So if one random order is selected, what is the probability that the order was from restaurant B or was accurate? First of all, I don't know how many total orders I had. So the first thing I would do is I would start adding. So I'd probably add up the first row. That adds up to 930. And then add up, you know what? I don't even need to add all the rows. Let's just add them all up. That might be easier. So if I add up all those boxes, I get a total of 1,029. So that's how many people I sent out to go through drive-thrus. All right, so we need to find the probability that it comes from restaurant B or it is accurate. Okay, are those mutually exclusive events? They are not, because you can order from restaurant B and get an accurate order. So that means we will have to use the whole formula. Probability that we get from B plus the probability that it's accurate, but we minus the overlap so that it is B and it is accurate. So probability of B, how many people? So restaurant B was 275 plus 29, so that is 304. So 304 out of the 1,029 plus the probability they were accurate. That's this first row, so I would add all those up, and that adds up to 930. So 930 over 1029, and then subtract that overlap, and the overlap is this right here. Right, the 275 that were B and accurate. Don't want to count those twice. All right, so that gives me 959 out of 1,029, and that is a decimal of 0.932. All right, so you got about a 93.2% chance that you're going to get an order that is either from restaurant B or it's accurate. But probabilities come in really well when you're playing card games. So you will find that there's a lot of examples of gambling. So if you're playing a game of five card stud with your friends, what is the probability that the first card dealt is a queen or a heart? So probability that that very first card, not any other card, just the first one, is a queen or a heart. So ask yourself first, can you be a queen and a heart? Yes, you can. So these are not mutually exclusive. So the formula we will need is probability of a queen plus probability that it is a heart minus the probability that it is a queen and a heart. All right, and we know there are 52 cards in the deck, so we'll just put those 52s all down there for our denominators. All right, how many queens are there in the deck? There are 4. How many hearts? There are 13 hearts. And how many queen of hearts are there? There is only 1. So that gives me 16 out of 52. And again, if they asked you to simplify that, the answer would be 4 out of 13. But most want that decimal. So my probability that it is a queen or a heart is 0.308. So you have about a 30.8% chance that the first card that's going to be dealt is a queen or a heart. All right, so take some time to go practice, and I hope to see you next time when we talk a little bit more about probabilities.